Lesson 10.4 Geometric Sequences and Series. A geometric sequence is a sequence made with a common ratio, which we'll call R, such as 1, 3, 9, 27, 81. So what it is, we multiply by the same things. We multiplied by 3, multiply by 3, multiply by 3, multiply by 3. So the ratio between any number and the one before it is 3 for this one. To get a rule for the nth term, let's say we take this 81, so that is our first term, the 1, times the 3 4 times. So that's the 3 is our common ratio. But 81's the fifth term, but I'm only multiplying by the 3 4 times, so that's 1 less than n. So our rule for the nth term is an equals a1, our first term, times r to the n minus 1. So let's find the rule for the geometric sequence 6, negative 2, 2/3. So the first thing to do is find r. So that looks like I'm multiplying by a negative 1/3. And again, I'd be multiplying by negative 1/3. So r is negative 1/3. And the a1 is 6. So an is a1 times r to the n minus 1. The second term of a geometric sequence is negative 18, and the fifth term is 2/3. Find the rule for the nth term. Well, really, we have 2 points. We know that a2 is negative 18, and we know that a5 is 2/3. But I don't know a1 and I don't know r. But what I could do is I could take the formula and I could plug in my point. So n is 2 and an is negative 18. So I can fill that in. N is 2. Oh wait, so that'd be negative 18 is a1 times r to the first. If I plug in my other point, the an is 2/3. Don't know a1, don't know r, but n is 5. So it'd be a1 r to the fourth. Well, I could solve this first one for a1. So a1 is negative 18 over r. Plug that in there. And so we'd have 2/3 equals a1, which is negative 18 over r, times r to the fourth. To multiply a fraction with a non-fraction, you just multiply across. Oh wait, and then we could reduce the r's. The r to the third. Divide by negative 18. And take a cube root. And so if I do a cube root, r would be negative 1/3. So now I can take that and plug it in there to find a1. So negative 18 divided by negative 1/3 is a1, which is positive 54. So our answer is an equals a1 times r to the n minus 1. All right, now if we talk about the series, the formula for the sum of a geometric series is Sn equals a1 times 1 minus r to the n over 1 minus r. If you want to see where that comes from, feel free to look it up. All right, if it's an infinite geometric series, it becomes a1 over 1 minus r. But that's when r is less than 1. The absolute value of r is less than 1. That's because r to the n approaches 0 if n is essentially infinity, if absolute value of r is less than 1. Think of r as being 1/2. When you square 1/2, it becomes 1/4. When you cube 1/2, it becomes 1/8. It gets closer and closer to 0. So if it's raised to the infinity, it would be 0. And so the whole formula simplifies to a1 times 1 over 1 minus r, or a1 over 1 minus r. If r is greater than 1, then there is no sum for an infinite geometric series. So let's evaluate this. Oh, hey, wait. How do I know that that is geometric? Well, geometric is in the form a1 r to the n minus 1. So this is exponential. It's exponential. If it's exponential, it means it's geometric. All right, so if we fit that little pattern, we can see our base is 2. I don't see anything multiplied by it, so think of it as being multiplied by 1, so a1 would be 1. So our sum is a1 times 1 minus r to the n over 1 minus r. Oh wait, what's n? N is up there, n is 7, so our sum of the first 7 run that through the calculator and is 127. Now let's evaluate this series. Well, we'll start here. That's our a1. To go from there to there, I multiply by 1/10. To go from there to there, I multiply by 1/10. To go from there to there, I multiply by 1/10. So r appears to be 1/10. So our sum, it goes plus dot dot dot. That means n is infinity. So our sum of an infinite geometric series is a1 over 1 minus r. Well, a1 is 5. 1 minus r is 1/10. 1 minus 1/10 would be 9/10. So we would multiply by a reciprocal, so it would be 5 times 10 over 9, which equals 50 over 9. And that is one way you can turn repeating decimals into a fraction. Oh, here's another infinite sum. All right, looking at, wait, what? We have a couple problems. One problem, that is not n minus 1, and the lower limit is not 1. We have to fix both those problems before we can actually use the formula, because this formula is only for when it's ar to the n minus 1, and it starts at n equals 1. All right, so the simplest thing is we can change the lower limit. We can just plug in the 0. So if I plug in the 0, I'll have 5 times 1/2 to the 0, plus, and then I'd plug in the 1, and then the 2, and then the 3. So if I'm plugging in the 1 next, that's the same thing as that. So it's just the sum from 1 on further. Okay, so that's easy enough. So that's 5. Now, how to change the n to an n minus 1? Well, what do we do to subtract exponents? To subtract exponents, we end up dividing with the same base. All right, so I'm going to take my 1/2 to the n, and I'm going to divide it by 1/2. That way, I'll have n minus 1 after I do the division. But I can't just change the value of the thing, so if I divide by 1/2, I have to multiply by 1/2 also. Because when I multiply and divide by the same thing, it cancels out. So I haven't changed anything, I've just changed how it looks. So this would become 5/2, and this would be 1/2 to the n minus 1, because I subtract the exponents. And now we can see we have a1 and r. So our formula is a1 over 1 minus r, but I have the plus 5 in front of it, so I still have the 5 added in front of it. So a1 is 5 over 2. R is 1/2. Go up here so I have space. Okay, so I have 5 over 2. 1 minus 1/2 is simply 1/2. Dividing fractions, so multiply by the reciprocal. And you see the 2's cancel. I have 5 plus 5, which is 10. So our sum is 10. Which you might notice would be exactly the same thing we get if we just went ahead and mistakenly plugged that into the function to begin with. Because starting at 0 with just n as the exponent happens to be the same thing as starting at 1 with n minus 1 as the exponent.